we're looking at rates of change, section 3.7. Here is the function S, the position of a function at any given time, t. And there are two questions. At what time does the particle have a velocity of 25, looks like meters per second? And we're going to find the solution to that. And the second one, when is the acceleration 0? So let's solve A first. If you want to get the velocity of a function at any given time t, you just differentiate its position. So 4t cubed, take away 12t squared, take away 72t plus 25. And we're trying to solve when is this velocity equal to 25. So really we've got an equation to solve that looks like this horrible mess. So let's see how that works. I have a technique called as long as you do it to both sides, it's okay rule. Any suggestions for what I could do to both sides in this equation to get it closer to being solved?
Subtract 25 from both sides.
And I would agree, it's a good start. And it comes out 0. Okay. What do you think I should do on the left-hand side to get closer to where we need to be?
Factor out a t.
Anything else while we're doing it? Any
40.
numbers? Yeah. So try, if you can, try and do the best you can. So what's that going to get me? A t squared, a take away a 3t, and a number which I'm trying to do in my head right now is 1, 8. Agreed? 18. Now, you have a quadratic. Agreed? And this quadratic is t plus somebody and t take away somebody. Agreed? What's the particular combination that we're looking for here?
Minus 6 plus 3.
And now we have some possible, and I use the word carefully, possible solutions. T equals 0, t equals -3, and t equals 6. But only 2 of those are actually usable.
0 and 6.
Why are we kicking out the other one?
The negative reference time is kind of weird.
Yes. And they also give you a little clue. When you read the question, they put that little t greater than 0, just to remind you. I also have to be careful here because I want to make sure I'm doing this exactly the way it's phrased. Yes. When you write your answers into the box, you know, the WebAssign format can sometimes be a bit clunky. You're only asked to put 0 and 6. So don't type in, I don't know, t equals 0, comma, t equals 6, because if you do that, I'll probably tell you you're wrong. So just a little hiccup. Now, that was doable because the numbers were really nice. But in question B, we're going to get an equation that you can't really solve algebraically. This was algebraically, right? You have to do it using Desmos, essentially. So I'm going to show you how we could do the same question we just did a second ago, which I like the way this is done because it's pure algebra. And we're now going to do it on Desmos. So I'm going to have, oh, can you see Desmos? Okay, so we've got S equals t to the 4, take away 4t cubed, take away 36 t squared. What else have we got? Plus 25 t plus, try that again, plus 25, right? And don't worry about how ugly it is, we'll sort that out later. And we want, and I just typed in the wrong one, didn't I, to put in the position? I told you to keep an eye on me. It's the derivative that we have to make 25, not the original function. So it's 4t cubed, take away 12t squared, take away 72 plus 25. That's the first one. And then the second one is we're looking for when the velocity is 25. Oh. And now I'm going to go to this guy. And I should have, why is that going weird? Hey, don't you dare do that. I'll try this again. I just want a horizontal line called v equals 25. Okay, if you're not going to cooperate, I'm going to make you cooperate. There you go. I called it y equals 25. Now, can you see the horizontal line meeting this ziggy-zag red line? If I scroll in, that guy there is the -3 that we didn't want. That guy there is the 0, and that guy there is the 6. You see, you can see where the blue line meets the red curve. Now, you could shrink the scale to see all the curve, but don't you only care where they intersect? You don't need to know what else is going on. So that's how you would do that one. Now, on the second question, they want to know when is the acceleration 0. So I'm going to differentiate this. And so you differentiate it, the velocity function, and you get 12t squared. Take away 24t. Take away 72. And we need to find out when it is equal to 0. So if I scroll this guy, one of the answers is about -1.64, and the other answer is 3.646. That is the guy you're looking for. That's when this is 0. Won't we kick out the -1.6 time because negative times don't make sense, right? So you could find out when the velocity is, let's say the question was, when is the velocity 10? The velocity is 10 at 3.799 seconds. When's the velocity? I don't know, some ridiculous 5.678, whatever. And the answer to that will be at 3.734. Can't you solve any quadratic polynomial equal a number by just putting in the polynomial here and the number here and finding out where the horizontal line meets the curve? So if you've got really ugly equations to solve for, rather than do them algebraically, I think Desmos is a much cleaner way to do the answer, right? Are we cool with that? That Desmos can help you solve equations that you couldn't really do algebraically. And it even does ones you could do algebraically as well. And let's return now back to our questions. So that was essentially 3A. 3B ended up being roughly 3.65, if you rounded it off, seconds. And then it gave you something that would only probably matter for those people who've actually done any kind of engineering or in physics class. When the acceleration is 0, in this case at 3.65 seconds, something is happening with the velocity. And isn't the velocity changing? And it's changing from being positive to negative, or from negative to positive. Same kind of thing could have been asked about the velocity. Suppose you found out when the velocity was 0. When the velocity is 0, isn't that something is changing from a positive velocity to a negative or the other way around. And can you imagine it's going up the way, positive velocity, then it reaches 0, and then it comes down. You see, that would be an example of what is happening at the velocity being 0. At that one instantaneous point in time, is it there a changeover from one type positive to the other type negative? An acceleration of 0 is the same thing. So I believe in my case, that's the last dot of the set. Okay, so question.
Does that only apply to that kind of a point where it's the top of the curve, or does that apply to any kind of a,
No,
it's when the function, the
yes.
slope equals 0.
Yes.
Okay, I see. Thank
Okay.
you.
Well, you just verbalized it and answered your own question, which is always good. Now, the next thing we're going to look at is a guy called the average rate of change. And so our first example is going to be a guy like question 4. And we're talking about, in this case, the area of a circle. So that's going to be A equals pi r squared, okay? And we're being asked to find the average rate of change, And it's going to be from 5, a radius of 5, to a radius of, say, 6. And so here's the formula for getting the average rate of change. It's the value of the function at B, take away the value of the function at A, divided by B, take away A. Does anybody recognize that guy? Because we didn't call it the average rate of change the last time we used it. What is that guy?
There's average values.
It's very close to average value. Yeah. You could get it in that case as well. Isn't that rise over run? Right. So the average rate of change is the value of the function at B, take away the value of the function at A, divided by A, B, and A. Right. So in this case, it's going to be the area of a circle at 6 seconds, or a radius of 6. The area at the radius of 5, divided by 6, take away 5. And you could get these answers as decimals, but don't. Use exact values. So when the radius is 6, pi times 6 squared is 36 pi, and pi times 5 squared is 25 pi. And one away from the other, I believe you get the answer 11 pi. So that's the one that they want you to put in, not 33.4 or whatever that might be as a decimal, but as 11 pi, right? So how do I know they want that? If they wanted decimals, they would say to 2 decimal places in the question. If you don't see any reference to round off to 2 decimal places, then you know it's an exact value. Right, and that might mean that the next answer is the square root of 7 pi or something, right? Whatever it is, that's what you're going to have to deal with. Now, if you can imagine the rate of change, they're saying, look, that from a radius of 5 to a radius of 6, this circle is increasing by 11 pi, whatever it is, square units. And you could do it from 5 to, say, 5.1. So there would be A and there would be B. And if you wanted to find the average rate of change, in this case, it would be the area at 5.1, take away the area at 5 over 5.1, take away 5. And this horrible guy is not pretty, but it does exist. I just need my calculator to do it. I keep losing my calculator today. There we go. Keeps hiding from me. So 5.1 squared is 26.01 pi. take away 25 pi divided by nothing point 1. Okay, that ends up being 1.01 pi over nothing point 1. And then I'm going to figure out what that looks like as an exact fraction. So 1.01 divided by nothing point 1, and then just go into math and turn everybody into a fraction, and you get 101 over 100 pi. To finish this question, they ask you to find that guy, which is question B. Aren't they finding the derivative evaluated at 5? Now, if you differentiate this guy, you get 2 pi r, agreed? R is the variable power rule, 2 pi r. At the 5-second mark, 2 pi 5, and this is called 10 pi. When we use derivatives like that, we very often call it the instantaneous, not sure you need a U there, rate of change. I think that's how you spell it, instantaneous rate of change. And isn't velocity the instantaneous rate of change of distance with time? Isn't acceleration the rate of change of velocity with respect to time? So instantaneous rate is just another jargon for the derivative, isn't it? Because that's what we're finding. So if you're given any formula and they say to you, find the instantaneous rate of change of whatever that thing might be, right? You can do that, right, by just finding the derivative. Do something for me, leave this question, and write this guy down again. The rate at which area is increasing is 2 pi r for a circle. If you want to visualize, what on earth could that look like? Can you imagine a circle of radius r? If that circle got a little bit bigger and it got that big, if I sliced that and made a long rectangle out of it, can you imagine me doing that? That long rectangle would be 2 pi r. Wouldn't it be the circumference of a circle? Does it make sense that a circle increases instantaneously by its circumference, right? If you're a big circumference, your area increases by more than when you're a little circumference, right? And that's kind of visually, if you like, what you're being asked to do. Suppose you're being asked to do the instantaneous rate of change of the surface area of a sphere, which is this guy. Then you'll find its derivative. And if you want to know its rate of change when it's, say, 3, you get that. Suppose I tell you that the volume of a sphere is 4/3 pi r cubed, and I want to know the instantaneous rate of change at 4 feet. Well, the derivative is multiplied by the power, reduce it by 1. You want to know the instantaneous rate of change when r is 4 feet. It's 4 pi times the radius squared, and the answer is 64 pi. So if you want to find the instantaneous rate of something, don't you differentiate it and then plug in the value? In this case, plug in r is 4. In this case, plug r is 3. In the question up here, plug r equals 5. Are we comfortable with that kind of question? You want to know the instantaneous rate of change? If you want to know the average rate of change, don't you end up using this guy instead? This is the average rate of change. But if you want to know the instantaneous rate of change, it's all to do with calculus, right? Differentiate me, plug in my number, get my answer. And unless there's a mention in decimal points, exact values only.
I have a quick question.
Mm-hmm.
Does it matter what you choose for A or B? Do you just choose the biggest number? Can you-
Choose the biggest, yes. So A is the little guy and B is the big guy. Right. That's the convention. If you accidentally get them back to front, as long as you're consistent, you get the same answer. But it's better to do small guy than to big guy. Are we good to move on to the next group of questions? Instantaneous rate of change just means find the derivative, plug in the number. Average rate of change, use a different formula. Now, here is a cool story. A tank holds 5,500 gallons of water, and the volume, well, there's a leak in it. And so the volume at any given time t is given by that formula. I'm reading here because I couldn't remember its name, so I'm glad they told me. This is called Torricelli's law. So if you imagine a big tank, started off completely full, right? And then there's a hole in here and out spurts the water. And at 1 second, 2 seconds, 20 seconds, the water is going down, right? So the total volume of water left in the tank after t seconds is given by this expression. So far, so good. That's just describing what's going on. And we are now going to find the rate at which water is draining, right? The rate of change at various values. Let's find the rate of change at the 5-minute mark. Well, I'll start with my formula. And I'll have to find its derivative. And this is the guy I'm going to use for all the questions up to question D. Ooh. If you want to differentiate this guy, couldn't you FOIL it all out and get a really ugly quadratic? I wouldn't. I would leave it as is and do a chain rule. So let's see what it would be. 5,500, right, somethings, multiplied by 2, right, multiplied by the power, and reduce the power by 1. And then, shouldn't you finish with the derivative of the inside function? What is the derivative of 1 take away 1/50th t with respect to t? What's the derivative of this guy, little guy here?
-1/50.
Agreed. And then I take this guy and this guy and this guy and find out what they end up when you put them together. So it's going to be 1100 divided by a 50, and the answer, try that again, 1100 divided by 50, and the answer ends up being -22, 1 take away 1/50t. So we now know the derivative. We now know the rate of change at any given time. So you want the rate of change at 5 minutes? It's -22, 1 take away 1/50th times 5, which I believe is a 10th, and that's 9/10. So if you came back to that tank and you put some kind of pressure meter on the hole so that you could register what rate the water is coming out at, it's coming out at -19.8, -198. Sorry, I got my decimal points right. Same digits, -198. There we go. -198 gallons per minute. Why is it negative? Not, I guess, positive is the other choice.
because it's going down. It's
Right.
leaving the box or tank.
Right. And big numbers doesn't it mean it's like gushing out like a bloody bullet, like fire hose kind of speed. And a very small negative number would mean it would be trickling out. Here is a very interesting one. I'll tell you the answer. At the 50-minute mark, the derivative, the rate of change, is 0 gallons per minute. What's happening?
It's empty.
Physically, it's empty, right? No more water. End of story. Are we good with that one to do with tanks coming up? Now, the next couple of questions, you kind of need to know a little bit about the storyline. At what time? So we'll only need to know the time. At what time do you think the water's going to be shooting out that tank at the fastest amount?
Sorry, what was that?
At what time do you expect the water to be coming out of that tank at the fastest amount?
The initial start.
Right, so agree at t equals 0, it's shooting out like a bullet. And the slowest is at t equals 0, right? So at time and at 50, right? And so even if you don't know physics, don't you know, at least if you tell me the equation of what's going on, can we use that in calculus to find out all sorts of things? Like, I wonder how fast the water's coming out in the 10-minute mark. I'll just do one of 7 because there's a lot of them. This one has decimal places to it, so you're going to do it as a decimal. D of t represents the height of a wave, and it's given by 7 plus the cosine of 0.503, then another bracket, t take away 6.75. And I'm just going to rewrite this even uglier. So 0.503 times 6.75. Now, whenever you get really ugly equations, the chances are the reason they're really ugly is that they're from real life data, right? And normal real life data is never 2t and plus 5s, right? It's always ugly decimals. Well, at least there are a couple of nice numbers, but mostly ugly decimals. And we are going to find the height that the tide was rising at any given time. So I'm going to find the height at time equals 6 a.m., which ends up being I believe 6. Check on that, sure it is. Yeah. So I need to find the derivative, and that's going to be the hardest part. Differentiating the number is gone. 5, that's a 5, cosines. If you differentiate 5 cosines, don't you get -5 sines of this ugly expression? So if you differentiate 5 cosines, you get -5 sines. There's a chain rule with some really ugly numbers. Instead of 2t plus 1, it's 0.50 blah blah t. But when you differentiate the inside function, you multiply by 0.503. Are you comfortable about where that guy came from? So if you differentiate this, you get 0, -5 sine of this, times the derivative of this, which is what the 0.503 gives us. And I'm going to put these together now as a 5 times 0.503. And now we have 2.515 There's a negative in front of it. The sine of 0.503 t, take away 3.39525. Okay, you want to know what it's like at the 6-second mark? How's the tide changing? It's this guy. (0.503 times 6, take away this guy. And you're just going to trust me because I've got the answer in front of me here. It ends up being 0.93. Whatever the units happen to be. So it's, here's a function, differentiate that function and then evaluate it at some number. Still a rate of change, it's just a really ugly sine function. Any questions about number 7? I mean, it's just ugly. It's, you know, ugly numbers. The method's not ugly.
Okay, I have
Suppose,
a question.
yes,
So is what we found the rate of,
yes, it's
Okay,
the rate
great.
at which the tide is changing.
and
So
then
it's
if you
changing
wanted,
at 0.93, I don't know what the units are. Oh,
sorry, that's loud. And if you wanted the height, it would have been just the original equation.
yeah.
Okay.
So if you plug in, see here that the height of the wave, and this here is, it's meters per hour. Well, that's, the tide is right. So if you were sitting just passing the time, watching the tide go up, and it was 6 a.m. in the morning, you would be seeing that the tide was rising almost a meter an hour, right? You could watch it, you know, a meter, a meter, a meter, right? It would be going up like that. If you just plugged in 6 here, this would be where the tide was as you looked at your watch at 6 a.m., right? So if you plugged in 6 here, you'd get the exact value of the tide. And this here is how it's changing through time. So in this case, the tide is increasing. I guess that means the tide's coming in. Question 8 has 2 problems to it. The first one looks like there's no possible way of doing this, but we're going to do it. Suppose that the population of a bacteria triples every hour. Okay, and that you start off with 700 bacteria. We need to create a formula for the number of bacteria after T hours. So it's every hour, right? Well, it's going to be 700. If the bacteria triples every hour, are you happy about 3 to the power of T? They never gave you that, but we are creating it. Right, if something triples, right, 3 to the power of 1, 3 to the power of 2, 3 to the power of 3, right? It goes times 3 every hour. So that's where this came from. So 700 times 3 to the T. And I put a little bracket around that to emphasize it even more. Now, if you want to find the rate of change, you have to differentiate this guy. So it's going to be 700 times 3 to the T. And what do you get when you differentiate a 3 to the T? Should be in that little list that I don't have handy, where I wrote down what you get when you differentiate a log to the base 3, or in this case, a power. It starts with times.
And then 3.
I think that's what she was saying, but it broke up. Natural log of 3. There's your guy. 700 3 to the T times the natural log of 3. If you were doing the log to the base 3, wouldn't you get 1 over, you know, whatever, T time, 1 over T times log 3 on the bottom, right? Bottom it's a log, top it's not. Okay, let me do it over here. If you differentiate this guy, you get 3 to the x log 3. If you differentiate this guy, you get 1 over x natural log of 3. Do you see the logs in different places? This one's on the top, this one's on the bottom. Right. That's the guy we're using. Right, this fella here, you're going to plug it into your calculator and round off to whatever it says, nearest whole number. So if you want to find out what's the rate of change 1 second, it's going to be 700 times 3 to the power of 1 times the natural log of 3, rounded off to nearest whole number, because, well, bacteria's come in unit values. And that's about 2,307 bacteria. Are we cool? Right, so that's how many more bacteria are going to be there after an hour has gone by. Right, it's not the total number of bacteria, but how many more they're going to be. It's going to increase by over 2,300. Number 9 is just a function, differentiate it and plug it in. So we are finished with that section, I hope. We're now moving on to a new section, which sounds very similar. And in some ways it is. Whoops. 3.9. And we're going to be looking at what's called related rates. So we've done rates of change. We're now going to do related rates. So things are going to change a little bit. Show you an example of it. The area of a circle is given by pi r squared. So I want you to imagine that we've got a circle and this is its radius. And I tell you that the radius is increasing at 5 centimeters per second. So if you're told the rate at which something is increasing, you're being told the derivative of it. So the rate at which the radius is increasing with time is 5 centimeters per second. And we are going to see if there's a way that we can find out the rate at which the area is increasing with time. So we're not going to find dA by dr. dA by dr is 2 pi r, right? We've done that. What we're going to think of is that this formula, each of the variables, the a and the r, are themselves functions of time. In other words, they change through time. And if you want to find the rate of change of this guy with respect to t, you have to employ this thing called related rates. So let me show you how it works. You differentiate this guy with respect to t, and you will get the derivative with respect to r times the derivative of r with respect to t. That is the related rate formula. Do you notice that this guy is made up of two things multiplied together? In a lot of ways, isn't it kind of sort of like a chain rule? Right? Not the same, but kind of sort of. So I want to find that when I know this. So if you differentiate a with respect to r, you get 2 pi r. And the rate at which the radius is fixed is 5. And so the answer is 10 pi r. So if you were being asked for the formula for what is the rate at which the area is increasing, dA by t, it would be this. But very often they add something else. they also tell you what R is equal to, in which case you just do a little bit more. And unless they ask for decimals, there's your answer. So some of the questions, you are going to be given a formula. The variable here and this variable here are going to change with time. You'll be given some information that allows you to use it. And then you will differentiate with respect to time using this formula. Tidy it up a little bit. And if they tell you R, you'll plug it in and use it. And if they don't ask you, that's your answer. And if they do tell you what R is, this is your answer. Okay, try another one. Suppose I know that the volume of a sphere is 4/3 pi r cubed. But this sphere is increasing with time. And I'm telling you, the rate at which the radius is increasing with time is 5, I don't know, miles per second. How about that? So it's a supernova, right? It's gone boom, right? It's exploded in front of you. And we are being asked to find the rate at which the volume is increasing when the radius is, say, 10 miles. So you get one of those dwarf stars that's crunched away to nothing and then it explodes, kind of the last thing that they do, right? Some suns, when they die, basically shrink. And then they get to some point where they just can't handle it anymore and they just blow up like like a grenade. So that's kind of what my model is like. So if you want to find dv by dt, it's going to be the derivative with respect to r times dr by dt. You see, I'm using the related rate formula, right? One derivative times the r. And if you look really carefully, can you kind of see where the answer's coming from? You see these guys cancelling out? R and R. Now, if you differentiate this guy with respect to V, you multiply by the power and reduce it by 1. So you get that guy times 5. So the answer is 20 pi radius squared. And if that's all they wanted, you're finished. But we want to know what's happening at one particular point when the thing's 10 miles. Well, the rate at which the volume is increasing is 20 pi times the radius squared. And it's that. And what's the unit's going to be? Well, it's a volume. So it's cubic miles per second. Right. That's what, about 6,000 cubic miles per second. Does that not give you an idea? This is blowing up really fast, right? 6,000 cubic miles is a lot, right? In a second, right? What's that? It's not the Earth. Let's say Earth 3,000 pi r cubed. Okay, it's about 2% of the Earth in a second, right? So in 50 seconds, it's grown to the size of the Earth. So this thing is moving. Let's turn that question on its head. Suppose we have 4 pi r cubed again. But this time I'm going to tell you the rate at which the volume is increasing is 100 centimeters, cubic centimeters per second, right? So this thing's not growing at all fast. And I'm asked to find the rate at which the radius is changing when the radius is, say, 20 centimeters. So I'm not being asked to find this guy. I'm being asked to find the other one, right? Because there's two things that could be unknown, right? This could be unknown or that could be unknown. We've already done the ones where I tell you this guy and we're being asked to find that. Now we're going to switch it. You got this guy and you're now going to find him. You start off with the same. dv by dt is the derivative with respect to r times dr by dt. That's going to get me 4 pi radius squared times dr by dt. And the volume is actually a known number, so it's 100. Okay, what do I need to do to both sides to find the rate of change dr by dt? Got this thing. What do I need to do to both sides to just find out what this is equal to?
Divide by 4 pi r squared.
Okay. Now, since I'm sticking to exact values right now, there's not that much I can do to make this look pretty, but I can divide the top and bottom by 4. So there, that would be your answer. Which is, oh, and then you plug in 20. And that's 25 over 400. That's going to be a fun one to do. 25 divided by 400 and make it a fraction. Oh, it's much nicer than I thought it was going to be. Which is 399. It's about 140th of a centimetre a second, right? It's hardly moving at all, right? It's very small increase in radius. Okay, feels like a physics class today, didn't it? Velocities, accelerations, rates of change. But the crux of it was all derivatives being used in various ways. Okay, last name down for attendance and bye-bye. And if I forgot to mention it, the solution to your test, your midterm test, is now online in Canvas. So you can have a look at it. So,
I had a question about number 4
on what?
on the for the lesson that we did.
Oh, I'll find it. Let me see. I'll try and find it. There's 7, that's 8. Was it 4 from the beginning of the day? Yeah.
Yeah, for average rate of change.
Okay. Of course, it's the only one I can't find, but it'll be here. I'll keep going. Or not. Okay. For some reason, I can't find it. Have you got it handy?
Yeah.
What does it say?
It was the 1.0 pi over 0.1.
Ooh, I better find that one. That sounds like a specific calculation. What was the
Oh,
main
it's that page.
that page?
That-
Oh, okay.
Yes, right there, number 4.
Okay. Right, here we go.
So at the bottom, I can't see the bottom. Okay, so you got 101 over
Aye.
100 pi.
1 over 1, yeah, eventually. And I did that by plugging it into my calculator.
Okay. When
And
I put it-
I may have made an oops. No, I didn't make an oopsie there. Okay.
Because when I put 101.01 divided by 0.1 and made it a fraction, I got 101 divided by 10.
It could be me.
Is it?
Yeah, yeah.
Okay.
I just had 1 0 too many.